Good morning, my dear students. Today our discussion is going to be on equipotential surface. Okay, so please do remember, my dear students, in first chapter we discussed about electric charge. The entire chapter was based on electric charge. Many concepts we discussed on electric charge only. And in second chapter we have been discussing on electric potential. Electric potential is a very important and interesting concept on which most of the times the questions have been appeared in competitive examinations as well as board exams also. Okay, I can say this potential is a darling of question paper setters. Okay, so many a times the questions have been appearing, so it is very important. If you have any doubt, you can ask me through your comments regarding electric potential. Okay, so let us begin our discussion on equipotential surface. You can observe the title itself. Equipotential is there. When you split this, you are going to get equal and potential. It means on the surface the potential is going to remain same. Okay, at all the points on the surface, if potential is same, then that surface is called as what? Equipotential surface. Very simple definition: the potential at all the points on a surface is same, then the surface is called equipotential surface, or it is also called as equipotential surface. See, for example, if I consider a test charge, a very small charge, plus q, okay, the direction of plus q will be radially outward like this. Okay, the field line will be always radially outward for a point charge, for a isolated point charge. Okay, and for this point charge, the potential surface, equipotential surface, should be in such a way that the surface should have potential same at all points. Okay, so for that I will consider a sphere this way. This is a sphere, and you can observe here from this point to this point. Okay, this is radius. Okay, and this is radius. Since radius is same, the potential is going to remain same at all the points. If I consider this point as A and this point as B, this A and B points are located at a same distance from plus Q, source charge. Therefore, potential at A and potential at B is same, or potential at this location, potential at this location, at this location, at this location. All the surface, throughout the surface, the potential is going to remain same because the distance is same. And as we know, potential formula is V is equal to 1 divided by 4 pi epsilon naught Q divided by R. If this distance is same, then the potential is going to remain same. And the point is, if you walk away from the source charge, the potential is going to decrease. Okay, if I consider one more sphere this way, okay, say at this point the potential is 100. At this point the potential is going to decrease, because as R increases, potential go on decreases. So potential is, say it is 80. If I consider one more sphere, okay, concentric spheres these are, with this Q as a center. Okay, and if I consider this sphere, then the potential is going to be 60. Potential go on decreasing as you walk away from the source charge. Okay, so these are the equipotentials for source charge, I mean the point charge. Okay, what is the shape actually? This is concentric spheres. Concentric spheres with Q at the centers is equipotential surface for point charge. Okay, no problem. If I consider negative charge, then negative q, okay, the direction will be radially inward like this. Okay, since the charge is point charge, okay, isolated point charge, therefore the shape will be once again sphere, concentric spheres, this way. Okay, see, at this point, or at all the points, the potential is same. But the fact is, if you consider another sphere, okay, another shape, another surface, the potential changes. From the surface to surface, the potential go on changing. But on a same surface, the potential always remains constant. Okay. So this is for point charge. What is the shape of equipotential for a point charge? It is concentric sphere, okay, with Q at the center. Okay. If you consider line charge, for a line charge means the charges in a line like this. These are the charges. During the electric field discussion, we have studied this one. Okay, so this is a line of charge. There are several charges here, and the shape of equipotential will be like this, and the direction is once again radially outward. This is the direction. Okay, and to say equipotential, okay, what is the point? The point is, throughout the surface the potential has to remain same. Okay, so for this linear charge distribution, we can consider a cylinder. Okay, so this is a cylinder. See, you can observe here this point, okay, let us call it as A point, and this point call it as B. Okay, the point A and point B, which are located at the same distances, okay, because the radius is same. Okay, therefore at this point the potential, and at this point the potential is going to remain same. The potential at this point due to this charge, and the potential at this point B due to this charge, it is going to remain same. Okay, you can consider one more cylinder like this. Consider one more cylinder like this. These are concentric cylinders. Okay, so the shape is shape for line charge distribution. Line charge, it is concentric cylinders. Concentric cylinders with line charge at the axis of cylinders. Okay, this line charge itself is an axis for the cylinders. Okay, so this is the shape of equipotential for line charge distribution. Okay, for a uniform electric field like this, these are the electric field lines. Okay, in such type of distribution, okay, the direction, I mean the equipotential surface will be normal like this. Okay, say this is a surface 1, this is surface 2, this is surface 3. Okay, if you take the surface 1, okay, if you take the surface 1, the potential at all the points are going to remain same. Throughout the surface the potential is going to remain constant. Okay, potential at one surface, second surface and third surface is different. It changes from surface to surface, but on this surface only the potential is constant. At this surface potential is constant. If I say the potential at first surface is 100, Okay, throughout the surface the potential is remain 100. If I consider at potential at the second surface the potential is 80, then throughout the surface the potential is going to remain 80 at this point, at this point, at this point, at this point, at all the points throughout the surface the potential is going to be 80. If I consider third surface the potential is 50, then throughout the surface the potential is going to remain same at this point, at this point, at this point. Okay, at any point on the surface the potential is going to remain, okay, it is 50. Okay, and point is these are the direction of electric field lines and this is the surface, these are the surfaces, and these equipotential surfaces should be normal to the direction of electric field lines like this. Okay, if I consider this as equipotential surface, then the electric field line will be like this. These are the direction of electric field line and this is the equipotential surface. The angle is how much? 90 degree. Okay, so remember this point. For a uniform electric fields, okay, for a uniform electric field, the equipotential surface will be normal, okay, or at a right angle. Equipotential surface is a plane. These are the planes actually, and these planes are at right angle to the direction of electric field. Plane surface is a plane perpendicular to E. Okay, so these are the some of examples of equipotential surfaces. Okay, for a point charge, the concentric spheres is the shape of equipotential surface. For a linear charge distribution, the shape is concentric cylinders. And for a uniform electric field, the direction, I mean the equipotential surface will be plane perpendicular to the direction of electric field. Okay, so now let us start the properties, very important properties of equipotential surfaces. And the first property, very important property, no work is done in moving a charge, a test charge from one point to other on equipotential surface. On equipotential surface. Its meaning is, if I consider one surface, one equipotential surface, consider this as equipotential surface. Okay, then consider 2 points A and B. If you want to move a test charge from A to B, then there has to be no work done. Okay, because at this point and at this point the potential is same, then and then only I can treat this as equipotential surface. According to the definition, work done on a charge, on a test charge, in moving from A to B is equal to VB minus VA, final potential minus initial potential. But see, this is equipotential surface. Throughout the surface the potential is same, then VB and VA are equal. VB is equal to VA. Then and then only I can treat this surface as equipotential surface. Therefore, work done in moving a charge from A to B is equal to 0. Okay, because VB is equal to VA. Or I can treat this definition in other form also, because VB minus VA is equal to how much? 0. Therefore, across the equipotential surface, the potential difference is going to be 0. Okay, that is the potential difference. The potential difference across any equipotential surface. Any equipotential surface is equal to 0. Okay, for example, consider one charge, okay, plus Q. For this plus Q, the equipotential surface will be concentric spheres like this. Okay, if I consider 2 points here, let us say this point is A and at this point it is B. Point A and point B are at a same distance from plus Q. Okay, therefore at this point and at this point the potential is same. For example, if I consider the potential at A is 100, then the potential at B is also 100. If I consider one more point, say it is C, then the potential is same, 100. If I consider one more point, the potential is 100. If you consider any point on this surface, the potential is going to remain same. Therefore, the difference of any 2 points is going to be 0. That is VA minus VB or VB minus VA, VB minus VC. Anything if you take, then the potential is going to be 0. VA minus VB is equal to 0. Since the potential across the surface is same. Okay. And one more point, see here. If I place a charge, test charge at this location, say it is Q, okay, this Q will experience a force, that is electric force in this direction. This is electric force, that is F is equal to QE. Okay, F is equal to QE. And this Q charge is displaced through a distance, say it is dx in this direction. Okay, and the direction of displacement is tangent to the sphere. Okay, and the direction of electric force is perpendicular to this tangent. It means the direction of force, electric force, is in this direction. Okay, and the displacement is in this direction, and force and displacement have an angle of 90 degree. It means the work done formula is force into displacement. Force and displacement both are vector quantities, and they have dot product. Therefore it is Fs cos theta. Okay, theta is how much? 90 degree, and cos 90 is 0. 0 into anything is 0. Therefore work done in moving a test charge from A location to B location, it is how much? It is 0. Okay, very important observation here. And for this, remember, this electric force and the amount of force, external force, both have to be equal and they have to be opposite. That is electric force, F electric should be equal to F external, and they have to be opposite. Okay, for this we have to take this charge very slowly, very slowly. Okay, the speed of the charge should not change. Okay, and kinetic energy should not be changed. Okay, that condition is very important. And this is the very important concept. No work is done in moving a charge from one point to other point on equipotential surface. Okay. Okay. Next, second property. The direction of electric field. The direction of electric field is always perpendicular to the equipotential surface. Equipotential surface. See here. Once again, if I consider uniform electric field like this, the direction of the shape of equipotential will be like this, plane. Okay, and see here, this plane is perpendicular to the direction of electric field. Okay, therefore this is treated as what? Equipotential surface. Okay, see, the angle between this plane and the direction of electric field is how much? 90 degree. Theta is equal to 90 degree. If I consider other charge, plus Q, say it is plus Q, and the equipotential surfaces are in the shape of concentric spheres, and the direction of electric field will be radially outward like this. Okay, see here, this is the direction of electric field and this is the surface. Okay, the angle is how much? Tangent actually. This is tangent and this is electric field. Angle is how much? 90 degree. If you consider any other point, see here, if you consider this point, this is the direction of electric field and this is the tangent on equipotential surface. Angle is how much? 90 degree. Okay, so it is always remain 90 degree. For example, if you consider line charge distribution, the shape of electric equipotential surface will be cylinder. Okay, see here, this is cylinder, actually concentric cylinders. Okay, and the direction of electric field is in this direction, and the direction of electric field is perpendicular like this. If this is the direction of electric field, this is cylinder actually, and the direction of electric field will be like this. The angle between equipotential and electric field is how much? It is 90 degree. It is always 90 degree. Okay, through formula also we can prove it. See here, E is equal to minus dV divided by dr. Okay, or dV is equal to minus E into dr. Minus E into dr. So dV is what? Change in potential, and this change in potential across any equipotential is going to remain 0. As I have already told you, VA minus VB or VB minus VA is equal to 0. This is change in potential, and change in potential on equipotential is 0. Therefore, dV is equal to what? 0. Or E dr is equal to 0. It means this E and dr have a dot product. Okay, and the dot product of two vectors is 0. What is the meaning? The meaning is E and dr cos theta is equal to 0. Okay, if theta is equal to 90 degree, then and then only E dr is equal to 0. It means E and dr have how much angle? 90 degree. If theta is equal to 90 degree, then and then only RHS part is going to be 0, no? Therefore, theta is equal to 90. The meaning is E and dr are perpendicular to each other. E and dr are perpendicular to each other, where E is electric field and dr is what? Distance. Okay, so this is distance. This is distance actually, dr. Okay. So this is very important property. Second property. See, E is perpendicular to dr. The meaning is E is perpendicular to dr. The meaning is if this is dr distance, for this dr, E is at an angle of 90 degree. See, dr and E are at 90 degree. Okay. So this is a very important property, second property of equipotential surface. Okay. Next property, third property, the equipotential surface. Equipotential surface indicates the region of stronger or weaker electric field. Stronger or weaker electric field. See here, E is equal to once again minus dV divided by dr. So since dV is what? Change in potential, and change in potential is always constant on equipotential surface. Therefore, E is inversely proportional to dr, or dr is inversely proportional to E. Its meaning is the equipotential surfaces are closer for stronger electric field, and the equipotential surfaces are farther for weaker electric field. For example, see, these are equipotential surfaces. These are equipotential surfaces, and these equipotential surfaces are very close to each other. And I consider one more equipotential surfaces like this. Okay, and these equipotential surfaces are farther. Okay, this indicates what? The distance between these two is very large compared to these two. Okay, its meaning is at this point electric field is weak, and at this point electric field is strong. Okay, the statement is the equipotentials are closer for stronger electric field, and farther for weaker electric field. So therefore this is strong and this is weak. Okay, so this is also very important property, second property. So dr is inversely proportional to E. If electric field line the equipotentials are very close to each other, then the electric field is said to be strong. If the equipotentials are the gap between equipotential is more, then the electric field is said to be weak. And the next property, fourth property, no two equipotentials intersect each other. While discussing about the properties of electric field lines, we have discussed this property also. Two electric field lines never intersect each other. The reason is, if they do so, then at a single point the electric field will have two directions, which is not possible. Okay, in the same way, two equipotential surfaces will also never intersect each other. For example, consider this as one equipotential surface. Okay, this is equipotential surface, and one more equipotential surface like this. Okay, and for this equipotential surface, say this as first equipotential surface and this as second equipotential surface. The first equipotential surface, the direction of electric field will be upward, because the electric field is always perpendicular to the surface, equipotential surface. And for this surface, see here, actually this is first surface and the direction of electric field will be like this. Okay, and for second surface is like this and the direction of electric field will be like this. Okay, and this is electric field. Okay, see, this is electric field 2 and this is electric field 1. At a single point, okay, the electric field has two directions in reality, which is not possible. Okay, the reason is, if they do so at a single point, the electric field will have two directions at a single point or at a point of intersection. At an intersection point, the electric field will have two directions, which is not possible. Therefore, two equipotential surfaces will never intersect each other. Draw equipotentials or equipotential surface for a pair of positive charges. Okay, for this consider two positive charges. Okay, and the direction of electric field lines will be radially outward. First we shall draw the direction of electric field lines, then the equipotential surfaces. See, these are electric field lines, and electric field lines are radially outward like this. Okay, So for this the equipotential surface will be like this. You can observe here at these locations the equipotentials are little further, okay, and at this location the equipotentials are very close to each other. It means this is a region of strong electric field. Strong electric field. And this location is region of weak electric field. Okay, similarly this is weak electric field region and this is strong electric field region. Okay, and as we know the equipotentials are very close to each other for a stronger electric field and they are farther, the equipotentials are farther for weaker electric field. As we know dr is inversely proportional to E, and reason is very simple. See here, if I place a test charge at this location, okay, say this is positive charge, this is positive charge. If I place a test charge at this location, say it is Q, this charge, test charge, will experience a repulsive force in this direction, and similarly this test charge will also experience a repulsive force in this direction. This charge is experiencing two forces, one in this direction, another one is in this direction. Okay, therefore net force on this charge is less. Okay, for example, if this test charge is experiencing a 100 Newton force in this direction and this test charge is experiencing a net force in this direction with say it is 60. Okay, therefore the net force is 100 minus 60 is 40, approximately 40. Okay, therefore if I place a charge, test charge at this location, say at this location Q, then this test charge will repulse in this direction. Okay, force due to this charge, force on this test charge due to positive charge in this direction. Say if it is 60, then force due to positive charge on this charge will be in this direction, repulsive force, say it is 40, and 60 plus 40 is, it is 100. Therefore the total amount of force at this location and total amount of force at this location, these are different. Okay, therefore at this location electric field is weak, at this location electric field is strong. Okay, so remember these are the shapes of equipotentials for a pair of positive charge. For a pair of negative charge also same. Okay, and sometimes the question is draw equipotential surface for dipole. Okay, sometimes dipole will be asked. See here, for a dipole. Okay, and for a dipole, say it is positive charge and it is negative charge. Okay, and the direction of electric field line will be from positive to negative, like this. So these are the electric field lines. Okay, and see here the electric field, the equipotential shapes will be like this. like this. Okay, see here, the electric field at this location is weak because the equipotentials are not closer, and at this point the electric field is strong since equipotentials are very close. Stronger electric field, weaker electric field. Okay, so this is all about equipotential.